All right, last problem for this week. We have problem number 8. And problem number 8 says, when you have a common ion added to a solution, which we just went over, we can make a prediction what's going to happen with the pH. This time we're going to calculate what happens with the pH exactly. So we're going to calculate change in pH. We can predict it, but we can also calculate what it's going to be. And we all love to calculate, don't we? All right. So first of all, if you have a ammonia solution, and this last problem gives me an ammonia solution of 0.2 molar ammonia. Ammonia is a weak base, So as a weak base, that means it'll form an equilibrium. All right, it'll have an equilibrium associated with it. And I never write this in because I just find it redundant, but this of course is going to be connecting with water, and water is going to have, so I'll do it this time. So we have water, we're putting this in. And water can break down into H's and OH's. So when I do acid-base chemistry, I like to actually write my water as HOH. So what will happen is with the water, which self-ionizes, we saw earlier when I was talking about Lewis acids, and I used ammonia as an example, that ammonia has an unshared pair of electrons, which can grab a hydrogen. So if this water is broken, it self-ionizes, has some hydrogen in it, those hydrogens can connect to that ammonia and make NH4, and then you'd be left with some free hydroxide floating around going, what am I gonna do? I guess I'll have to make a basic solution. So that's what's going on here. I don't write the water in. It's always on the left side of these reactions. It always is. I just don't write it in because it just, to me, it gets kind of redundant. But on this one, it might be kind of confusing. How did you get NH4 and where'd that OH come from? Because the OH wasn't here. It's not on the ammonia. So where'd the OH come from? It came from the self-ionization of water, and that hydrogen connects to the ammonia and leaves it with some OH, which is going to make my solution basic because I'm pulling hydrogens out and leaving OHs. Okay, so ammonia solution, we start out with 0.2 molar. We start out with none of this before we get that dissociation. We don't have any. Then the change is negative X, positive X, positive X. At equilibrium, I get 0.2 minus X, X and X. I hope you can do these in your sleep at this point. You should be able to. The K value for ammonia, 1.8 times 10 negative fifth. Yeah, it is. 1.8 times 10 negative fifth, my K value for ammonia. All right, is equal to products. X is X squared over reactants, 0.2 minus X. That X is really small. Check the rule of 100. Remember, take your concentration, 0.2, divide it by the equilibrium constant, which is small. You're going to get a number bigger than 100. That X can go away. Okay? Makes the math a lot easier. No quadratic. So multiply those, take the square root. Multiply those, take the square root. X comes out to B. Now remember, this actually is going to give me the concentration of hydroxide, not H, so we've got to be careful of that. Did this earlier. What do we come out with? X comes out to B, 0.0019. 0.0019. Okay, now that is my concentration of OH. So just be careful, because we're going to do so many problems with H's and pH's. This time I have hydroxide, so that's my OH concentration. Okay, now take that, put it in to a POH equation. You can do that. There's a couple of ways to do this, but you can do it this way. POH is equal to negative log concentration of OH, 0.0019. So go ahead, hit your log button, log 0.0019, enter, get rid of the negative. You should come out with a POH of 2.72. Okay, 2.72. Now remember though, the question was not what the POH, the question is what the pH is. So that's not the pH, it's the POH. Easy, I can just take, I know that the pH plus POH must equal 14. Okay, pH plus POH must equal 14. So 14 minus 2.72 gives me the pH. I subtract those out, I should come out with 11.28. That should be 11.28. So that's my pH. Does it make sense? Of course it does. It's chemistry, hello. But it makes sense because the pH is 11, that's basic, which it should be. It's ammonia, it's a base. Okay, makes sense. Okay, that is straightforward ice chart. Now, here's the little kicker. There was an A and a B to this. Part B says, okay, what if you take this ammonia solution that's happy, loving life, and you decide to bust its bubble, throw some salt in that has a common ion with something in our reaction. All right, so what did we throw in? We threw in, we're going to throw in some ammonium chloride. We're throwing in 0.3 molar ammonium chloride. So we're throwing in this nice and happy situation ammonium chloride. Very soluble stuff, very soluble. Breaks down, so you end up getting this separated. You'll have 0.3 of this and 0.3 of this. Common ion. You're throwing in an ion that's in that equation. It's going to scooch with it. It's going to mess with it, man. So this is going to change things. Let's make a prediction based upon what we had learned previously. If we throw this in, this freaks out. It says this whole thing freaks out. So we got to get rid of this. Too much. How do we do that? Connect it with this. Throw the reaction to the left. So that means we are going to lose hydroxide in order to get rid of the NH4, which means if I lose hydroxide, I'm not as basic anymore. I'm not as basic anymore. That means I'm going to lose pH. I should go down in pH. So my number should be lower when I get an answer for this finally than the 11.28, which we just previously got. Okay, let's do the math. Should work. I have faith in you. Okay. This time, initially, now, we have added 0.3 of this to the equation because we start out with 0.2 of this and we're throwing in with it 0.3 of this. Now remember, that's a 0.3 of the salt, but that means when it disassociates, I have 0.3 of each ion, and 0.3 of that ion, I'm going to have that's going to matter. So I start out with, we take these and go 1, 2, 3, go, throw them together, 0.2 of this, 0.3 of this, 0 of this, okay, 0 of that at this point. Now, what's going to change? Okay, I'm going to lose this. Okay, we end up losing that over time. So as we lose this over time, okay, we're going to gain, and we're going to make some more of that. Let's go ahead and do this. What's going to change is the math. The only thing that's going to change in the end is the math. I mean, the whole situation is the same as last time, except that I have a number here instead of just an x. So it's going to be a little bit different math in the equilibrium expression. So the K value for ammonia is 1.8 times 10 to the minus 5. That equals 0.3 plus x multiplied by x. 0.2 minus x. These x's are very small. We've already determined this one is really small. This one we also can determine is really small. We use the same rule. I mean, sometimes people go, well, can I do the rule 100 on the top as well? Absolutely you can. So this x will be very tiny when I take the original concentration and divide it by that. I'll get a big number. So this x can also go bye-bye. All right, 0.3 divided by 0.2 is 1.5. So 1.8 times 10 to the minus 5 equals 1.5x. Divide by 1.5, we will get x. And that x equals Hold on to your butts. Jurassic Park. Coolest guy in movie history said that. Mine. Samuel L. Jackson. Okay. Samuel L. Jackson. I'm sorry. I'm going off on a tangent. This comes out to be a concentration of 1.2 times 10 to the minus 5. Okay, 1.2 times 10 to the minus 5. Oh, wait a minute. No, don't do that to me. No, close, thank you. Oh, sorry. Sorry. It was telling me my battery's getting low. It sure is. I'm getting tired. I need some food. Battery's getting... Let's finish this. That is X, which is this, which is my OH. Put it into your POH equation just like we did last time. So POH equals negative log 1.2 times 10 to the minus 5. Logify that, you come out with a POH of where is it? Wait for it, 4.92. Subtract that from 14. And you come out with a value of 9.08. Yeah, 9.08 is your pH. What happened? The pH originally, without the added salt, was 11.28. We added the salt, the common ion effect. We pulled some of these OHs out of the solution to deal with it. So we lost OHs, we lost bacidity. I like that word, I made it up, it's cool. Bacidity, and so we went down, and we came out with a pH of 9. Lower pH because we lost hydroxide. All right, that's the application mathematically to the previous problem. And that makes like a Christmas present or a holiday present. Don't want to offend anybody. Holiday present. And wraps it up.